My dear students, in the last class we discussed the automorphisms, inner automorphisms, and then we show that important results that inner automorphism is a normal subgroup of a automorphism of a group. This lecture we discussed the important theorem is a Cayley's theorem, which say that the every group is isomorphic to some permutation group of. So let's say any group G is isomorphic to itself under the identity mapping. We have to see the natural question whether G is isomorphic to any group other than itself, because every group is isomorphic to itself under the identity mapping. So the question is simply this: if G is isomorphic to any other group for other than the itself. So Arthur Cayley provide a classical theorem that answer this question affirmative. Cayley theorem represent a group as a subgroup of a permutation group and is up to an isomorphism. So I just state the theorem of Cayley as follows. He said that every group G is isomorphic to a subgroup I just denoted as a SG, where SG is a group of all possible permutations of elements of a G. So every group is isomorphic to a subgroup of SG, where SG is the group of all possible permutations of the elements of G. So now we have to first we prove this theorem, and based on this theorem we have to try to discuss some examples in this lecture. So let's first we have to try to prove the this theorem. So we have to show that this means every group G is isomorphic to subgroup of SG. So let G be a group. For as G belongs to G, we define a mapping phi G from G to G by phi of x is equal to quotient of a G by Gx for all x is the element of a G. That is, the image of all each x belongs to G is obtained by multiplying on by left by G. We have to writing into this form. So this is the mapping we have to just taking in this form. Then we have to define in a certain way, that means phi G map G to G, and we have to define image of each x belongs to G is obtained by multiplying x on left by G. So now we just say that first is this mapping is defined, and this map should be a well defined, and well defined means we take two different elements x is equal to y, and then x is equal to y means you have this G and this G is also the element of this G for each G belongs to G. So we have to multiply it with x and y are the element of a G. Then we have to write Gf x and Gy, and if Gx Gy is equal to this is phi of x and phi of y suffix G over with this element of a G. So this means this clearly we say that this map define phi Gx is equal to G of x, Gx is a clearly is a well defined map. So first we have to show that this map is clearly is a well defined map. Okay, now so we have to show that this map is also is a 1 1. So proof we have to taking this is trivial proof is not difficult for 1 1, because we have to show that 1 1 means we have to take a phi G x is equal to phi G y, and now you that as we take this phi of G of x is equal to phi of G of y, then the by definition this is nothing but is equal to you have a G of x, and this is nothing but is equal to you have a G of a y, and then because this G and x all are the elements of a group, and G is a group, and group hold all the cancellation law. So by the left cancellation law, this implies that you have said that x is equal to y. So clearly we can say that if we have a phi G x is equal to phi G y, and this means we can say that x is equal to y. So clearly this phi G is 1 1. Okay, now we have to try to form that this is also is onto. So for onto-ness, let Z be an arbitrary element in Z, and then this Z is the element of a X, then I just write it because G is the element of a, you know that G is the element of a G, and then we can say that G inverse Z is any arbitrary element of a G also. This is also the element of a G, simply because G is a group, and if G is the element of a G, then clearly we can say that G inverse is also the element of a G. So if G is the element of a G, then G inverse is the element. G inverse Z is also the element of a G. We are assuming that this is nothing but is equal to our X is there. If this is a X is there, then we can say that phi of G of X is nothing but is equal to, you know that this is equal to, you have a Gx, and then G of X you have to taking as the element of a G inverse X. So you have to take a G of G inverse X, Z, sorry, this inverse Z, and now because this G inverse Z, all are the elements of a group, and by the associative property we can say that G inverse Z, and then G inverse Z is equal to identity of a Z is equal to Z. So we can say that simply is equal to this hold, phi Gx is equal to Z, and Z is an arbitrary element of a Z, phi. So we can find that this phi G is a permutation on the set of elements of a G. So this means we take a this show that phi G is a bijective map, and then we have a permutation, means we have a function class of a symmetry, all the bijective function. That means we show that this phi G is nothing but is equal to is a 1 1 and on 2. This map is defined. If it is defined, this phi G is 1 1 and on 2, then first objective, this means phi G is a permutation on the set of elements of a G. That means phi G is the element of a belongs to the SG. S is a class of all the permutation. This means phi G, we have to show that this phi G is clearly is a map defined is 1 1 and on 2, and that is a bijective. If it is bijective, then we can simply say that this is phi G is a permutation on the set of elements of G. So phi G is the element of a SG. First thing we have to just say that means phi G is the that element of this is nothing but is equal to is the element of SG. Okay, now we have to define, because we have to show that there is a isomorphics from G to the permutation group subgroup. So he say that we have to take this is a psi of G to G SG, and then we have to just this is psi of G is nothing but equal to phi of G, and now we have to show that if we show that this is a psi to psi G to SG is a 1 1 onto homomorphism, and then we can say that G is isomorphic to this SG. So by this G is any group is isomorphic to this permutation of a subgroup of G, then we can say that simply the phi G, this psi of G is equal to defined. So first is again this mapping is a well defined. You have taken any two element, you take a simply you take a G1 is equal to G2, and then you can write in the form of a G1x is the same as a G2x, and then you can say that G1x is nothing but is equal to, you have a phi of G1 is the same as a phi of G2, and then this is nothing but is equal to, this is you have a psi of G1 is equal to psi of G2. So this means clearly we say that this map we have to define psi of G is equal to phi of G is clearly is a well defined. We take a G1 G2, then for all x, that means we can say that this is for all G. This means we have to show that clearly the first part of this thing. Clearly we can say that this means if this map we define clearly is a well defined map. So now we have to next show that this map is onto and homomorphism also and 1 1 also. So first we take a show that this is a homomorphism. So we take any G1 G2 belongs to G, then you say phi of G1 G2 by the definition of a this is can be written as a G1 G2 over X, and then because of this associativity, this can be written as a phi G1 over G, because you have a G1 G2 are the element of G, and X is also the element of this G, and this can be written, and now this is nothing but is equal to G2X can be this is nothing but equal to some element, and G1 of something elements of a G, this is also the element of a belongs to G. So G1 of this means we can say that this is nothing but is equal to phi of G1 over G2x, and now G2x is nothing but is equal to, you can say that this is nothing again, you have this phi of G2 of Gx, so this means can say that phi of G1 G2 x is nothing but is equal to in this form. Now for all x is the element of a G. Now but we have to show that this psi of G1 G2 is the same as the psi of G1 psi of G2. So we take a psi of G1 G2, and by the definition this is phi of G1 G2, and now phi of G1 G2 we have to show that this is true for all x. So this means we can say that phi of G1 phi of G2 is the same as a phi of G1 G2 for every x is true. So this means is a phi of G1 G2 is the same as a phi of G1 phi of G2, and then this is the same is a phi of G1 G2 is equal to phi of G1 G2, and now again by the definition of psi, this is nothing but is equal to psi of G1, and this is nothing but is equal to psi of G2, psi of G1 G2, then psi is a homomorphism. So we have to prove that this map is phi psi we defined from G to SG is a well defined map, and also we show that this map is an homomorphism. Now we try to show that this map is also is onto. If we have to success to prove that this map is also onto homomorphism, then we use the first isomorphism theorem, and then we can just take this. Okay, now we have to show that the definition psi is clearly is onto from the definition, because you have to just say that we have to define the psi of G you can is equal to phi of G, and then you have to phi of G is onto. So this means by every image of this. So by the definition, that is clearly psi is an onto. Now we have to show that finally this psi is 1 1. So we have to take a 1 1 means we take any two image of psi of G1 is equal to psi of G2, and then we have to show that G1 is equal to G2. So we start from this psi of G1 is equal to G2, and if psi of G1 is equal to G2 means we can say that this by the definition this is phi of G1 is equal to G2. You know that if phi of G1 is equal to G2 means we can say that for this is true for each. This can be written as a phi of G1x is equal to phi of G2x for all x is the element of a G. And now if phi of G1x phi of G2x, you know that you have a G1x is equal to G2x, and this is the all are the elements of a group, because G1 and G2 are the this is G1 and G2 is also the element of a G. And now here is the cancellation property hold. By the cancellation property, this can say that you can write in the form of a G1 is equal to G2. So this means we can say that simply we have a G1 is equal to G2. So we show that this means this map psi we have to take and define from S to this map we take this psi from G to SG, and then this is clearly nothing but is equal to this which we have to just say that by the fundamental theorem of a homomorphism, this can be said that G is isomorphic to image of a this this G. So this means psi of image of a psi of G is equal to this one. So this means by this we can show that we have a 1 1 onto and homomorphism. Then we can say that G is isomorphic to image of this psi of G. So this means this complete the psi of G, nothing but is equal to you have a S of G, and then we can say that simply we have a map defined in this form is clearly is a is isomorphic to a this group of a this form. Okay, now we have to conclude this by a very basic corollary saying that every finite group G of order n is isomorphic to a subgroup of Sn. Means it simply say that if we have a every finite group group G of order n, for example, if we have a group of order G is a group of order 2, then is isomorphic to a subgroup of Sn, means this G is isomorphic to subgroup of a S2, and then clearly we have to Z2 G order of a 2 is equal to, you can set as Z2, and Z2 is nothing but is equal to isomorphic to a subgroup of this S2. You know that the order of S2 is equal to, you have a clearly is equal to factorial 2. So this means isomorphic to S2. So Z2 is isomorphic to S2. S2 is only two permutation identity, and also one 2 is there. So you have clearly we have to define this. So this means we have to try to some examples later on. First try to this caller is saying that means every finite group G of order n is isomorphic to subgroup of Sn. Okay, let's we try to prove that this let G is equal to G1, G2, Gn, then if this is a group, let G be a group, finite group, and then the elements of a G is a G1, G2, Gn, then this that Cayley theorem say that assign the element of a Gi is a map that is isomorphic to some permutation group. There's a permutation group means is a phi of Gi is equal to G1, G2, Gn, and then we have a multiplied by element of some Gi, that we map phi of G we define as a G of X types. So this is a G1 we write in the form of this Gi, so Gi and G1, Gi, G2, Gi, Gn in this form. So this is we have to define into this form. And now since Gi, G1, Gi, G2 is just a ith row of the Cayley table for G, for a group G, and thus it's a simply rearrangement of G1, G2, G3 up to Gn, and then this is nothing but is equal to we simply say that this is nothing but is equal to this is G of phi I1, and this is a phi I2, and phi I, this is phi I is nothing but is equal to in the element of Sn. So we just say that this can be this arrangement of in this form. So this means this written in the form of this. So this means every finite group of order n is isomorphic to some subgroup of Sn. So we have to just into this form. Now since this capital phi I is equal to, you have a G1, G2, Gn, G of or phi I or phi 2 or phi, and in this form. Now if you see, if we replace Gi by I, we map phi I to this is nothing but is equal to Gi by I, so phi I1, phi I2, and then Gi by I, so this is equal to 1, I is equal to 1, 2 and 3, then this is equal to phi 1, phi I1, phi I2, phi I2, and this is nothing but equal to phi I. So you have a 1 goes to 1, 2, 2 and so on is a phi I. Then our Cayley theorem is saying that if this is nothing but phi I, then this element phi 1, phi 2 images are isomorphic to this psi G is equal to G. This means these are the isomorphic to some capital psi G, and psi G is nothing but is equal to, you have a is isomorphic to G. So these elements are that means G is isomorphic to a that is G is isomorphic to a subgroup of Sn. So this means by this we can simply prove that this is true for every. This means we can replacing, this is the very important concept we have to using Gi by I, and then means G1 is equal to 1, G2 like this. We have to replacing Gi by I means we have a G1 is equal to 1, and we have to take a G2 is equal to 2, and so on. We have a Gn is equal to n, and accordingly this you have a G, this is a G of phi, this is nothing but equal to G of 1, so this means phi 1, this is nothing but equal to phi I1, phi I2, phi I, and in this form we have to write in, and this means Gi is equal to 1, you have a phi of G you can define as a G of X types. So this means we can say this is image of this is nothing but phi of I. So this means by the theorem is saying that this is isomorphic to this map. So psi phi 1, phi 2, phi n is isomorphic to psi of G, and psi of G is isomorphic to G. So this means these are the isomorphic to this G. So G is isomorphic to this as some permutation group is there. So this is the complete the proof of the this corollary. Okay, now we have to this very important proof. We have to start with this very simple question is asking there. We say that verify Cayley theorem for a cyclic group G of order 3. You know that if we have we have giving the cyclic group G of order 3 means you have a G is the type of this is generated by some element G. So G we can say that, and G square and G in your order is equal to 3. So order 3 is equal to, you have clearly the identity. So this means we can clearly say that this the corresponding to a permutation group isomorphic. What is the corresponding permutation group isomorphic to G? That's the question. So this we have to verify the Cayley theorem cyclic group of order 3. Let G be generated by, so G is a group, cyclic group is generated by G, and then G is the element of G is the form of this G square G cube is equal to identity. And now we have to verify this. Suppose pi I is a we take this, then G1 is another group, is a form of this because corresponding this is a permutation group. So we just take for a this identity corresponding, we have to just say the pi of E, then corresponding pi A, and then we have a pi of A square. So G1 we choose another group which is a permutation group. So it's a permutation group, its permutation group we have to assuming that G1 is equal to pi E, pi A, pi of A square. Now what happened if pi of EA is equal to nothing but is equal to A times of E by the map we have to define because you have to just a phi of G of X is equal to, you have to the G of X. So we have a or X into G is not a problem, we have to just write it in the form. So this means we can write in the phi of EA, yeah, EA is not a problem, and then EAE is equal to we have just nothing but is equal to A and E are the element of this group G. So this means this is equal to identity. Now phi of E of A square, then we have A square identity is equal to A square, and then you have a phi of E is equal to this is phi of E over, we take a E, and this over E is equal to E into E is equal to identity. So this is phi of E is nothing but is equal to, you say phi of E is equal to this means you have a identity. So you have a if you have taken, if you write identity is equal to 1, and then we have to write A is equal to, you have a like this is equal to 2, and we have A square is writing the 3. So it's equal to 1 2 3, then this is equal to phi of E, phi of 1 is equal to 1, phi of A square A is equal to, you have a phi of E is equal to 2, and this is equal to 3, and this is nothing but is equal to is a identity permutation, and that is a phi of E nothing but is identity mapping from of G. So this means phi of E is nothing but is equal to, we have to just say that this is nothing but is a identity mapping of this group onto this form. Okay, so now we have to calculate the other form, pi of A is equal to A square, pi of A square, A into A square is equal to A cube is equal to identity. Now pi of E, now in this case if you see this means we have to changing this E is equal to, we have a 1, 1 A is equal to, we have to 2, and A square we have to assuming a 3. Then you have just see that 1 2 3, then identity, if you take identity is equal to 1, so this is equal to 2. If A is equal to A square, this is equal to 3, and then you have to just say that by A square this is equal to 3, this is equal to, you have a 1. So in this in this case you have to getting this if this is the another permutation elements in this form. And now if we have to just this pi of A square, A square is equal to identity. So if we have to just 1 2 3, and then A square is equal to, you have identity is equal to that means you have a so we have to give into this form pi of A cube is equal to identity, and then this is this is A square, okay, A, and then A square A over A square for A, and then you have a 1 2 3, then this is identity, then for A square is equal to A, so we have to A square is equal to A2, and then A cube identity for A square, this is equal to 3, then this is another property of this. this is pi of a square. Now pi of a it is observed that this G1 is nothing but is equal to this group is generated by pi of a. If you just see this, all the element is generated by pi of a. So this means clearly, since you see this means pi of pi of a, this is nothing but is equal to this, you have a like this is a 1 2 3, and now if you see this clearly you have a pi of a square can be written in the form of a pi of a ka whole square. Pi of e is nothing but is equal to, you have a cube ka whole cube. So this is are the same. So we just say that if you see this G1 is nothing but is equal to cyclic generated by 1 2 3, and then the element of this is nothing but is equal to generator E. You have a 1 2 3 and 1 3 2, and this is nothing but is equal to, you have a pi of I. This is you have a, and this is you have a E and G, and this is equal to, you have a G and G square are there. And then if you take a square of this is again, if you verify this, you have to take a 1 2 3, then 1 2 3, then if you are getting this thing, then is equal to 1 goes, 1 goes to 2, and 2 goes to 3, then 3 you have a 3 goes to 1 and 1 goes to 2. So this is equal to, you have clearly you have a 1 3 2 1 3 1 goes to 3, 3 goes to 2, 2 goes to 1, then it's equal to 1 3 2. So this means this whole thing is generated by these 3 elements. And now we take a group of order G is equal to group of order 3, and then the corollary say that this group of order is isomorphic to some S subgroup of generated by S3, and this is the subgroup of this S3. You have a G1 is equal to is generated by 1 2 3. So this means this order group group of order 3 is isomorphic to this G is isomorphic to subgroup generated by 1 2 3, and that is a permutation group. So this by this example we can very clear that means if a group finite order group is isomorphic to some permutation group. Let's try some other example. We take a order 3. Now we move to the some example for order 4. Let G be this group of order 4, and then we have discussed many times this group in these lectures. So this is the table for this group. I am not going to verify each and every table. You have identity element here, and you have a 1 and minus 1 are the self inverse, and I or minus I are the inverse to each other. So now we have to just say that this is a finite group of order 4. That means this is also is a isomorphic to some of the some subgroup of a S4. So we try found out where is this isomorphism is there. So just we have to take a indices of a 1 I minus I replace is a 1 1 2 3 4, and then it is a phi 1 is equal to, just take you have a, if we have a mapping to itself, phi 1 go 1 1 minus 1 2, and this is nothing but is equal to, you have a phi 1 is equal to identity. Now phi 2 is equal to, we just into this form, phi of 1 is equal to minus 1, and this, and then you have a into this form, and then in place of this we have to result into this form. This is getting into 2 1 4 3, and this is nothing only 1 2 and 3 4. And if phi 3 is equal to, you just check, we write into, because we have to taking the phi of G is equal to, you have a gx types element. Just similar fashion I have to calculate each and every element in this form, and then we have to calculating. So I just write directly. So phi 3 we just take a this is go to this, so the minus I, so 1 minus I, and then 1 goes to I minus I, and then we have to into this form by cyclic notations. We have phi 3. So this is a psi of small phi 3 is equal to nothing equal to 1 3 2 4, and this, and now you see this H is equal to E 1 2 3, and this is nothing but is equal to, this is a clearly is a, this is a, this H is clearly is a subgroup of a S4. So you can verify this is the clearly this is a subgroup of a this by this element of one form. So this means when index is 1 minus 1 I minus I, we just replacing this as a 1 2 3, and then we have to phi of 1 phi of 2 and so on. We define 1 2 3 4, this is identity. Then we have to similarly is equal to 1 minus 1 I minus I, and then we have to minus 1 and then 1 minus I and I, then we have to switching these two, and then similarly we have to all these things. So this way we can clearly find out this index of this replacing this form. Then this clearly H is a subgroup of a S4. Okay, now one more example we take. A V is equal to, we generally write in the form of a this, and now you know that we have taken the 4 elements 1 2 3 4, and then alpha square beta square is equal to identity, alpha beta is equal to beta alpha. You know that this is a very standard group, is a Cayley 4 group. Now if this index is E alpha alpha beta alpha, this is I replace as a by E alpha is equal to 1, sorry, E is equal to 1, then this index is into the this table. You just see I actually this I just say that I replacing into this form. This is a 1 1 2 3 4 5, and then we have to 1 minus 1. This is a this is I take a this element, then we have to next is letting into this form. This is the first is corresponding to this table. I just take a 1 2 3 4 4, and then this is equal to same 1 2 3 4. I just take a 1 sorry, this is equal to, I take a okay, 1 is equal to 1, minus 1 is equal to 2, I is equal to 3, and minus I is equal to 4. So I replacing here is just like this. So I take a in permutation form, this is equal to 4. Now second row, you take this second row, you have a 1 2 3 4, and now minus 1 is equal to, you have a 2 and then 1, and then you have a 4 and 3, and then you have to see 1 2 3 4, and then I is equal to, you have a 3, and then minus I is equal to 4, and then you have is equal to 2 and 1, and then last one you see 1 2 3 4. By this you have a 4, and this is equal to 3, and is equal to 1 and 2. So like this way we have to writing this all this phi 1 phi 2 phi 3 and phi 4, and that is nothing but is equal to this form, and that is clearly the subgroup. So similar fashion we have to here also, if you know that the Cayley tables of this by this, if you want to this we derive this is equal to, you have E alpha beta E alpha beta then E into E alpha beta alpha beta. Now you have alpha square is equal to, you have identity. Now you have alpha beta is equal to, you have a alpha beta, and then you have a now you have a alpha square is equal to identity. That means you're getting the beta. Now you have a beta alpha is the same as alpha beta, and then you have a beta square is equal to, you have a identity, and then you have a beta alpha beta, then alpha beta square, you have again alpha, and in the same of you have an alpha square, you getting is equal to beta, and then you have a beta square, you getting the alpha, and alpha beta ka whole square, you getting the identity. Now if you see in this form, we can just side writing is the form of this 1 2 3 4, and then identity is equal to 1, alpha is equal to 2, beta is equal to 3, and then 4. This is by this. And now for second we take a 1 2 3 4, and then alpha you have taking is equal to 2, identity is equal to 1, and alpha beta you taking is equal to 4, and then you have a 3. Now third one you have a 1 2 3 4, and then you have beta is equal to, you have to taking as 3, and alpha beta you taking as a 4, E is equal to 1, alpha is equal to, you have a 2. And now you have again for the this one 1 2 3 4, and alpha beta is equal to, you have a 4, beta is equal to, you have a 3, alpha is equal to 2, and then 1. So we getting is this this 4 permutations in this by this table, if we replacing E alpha beta and alpha beta by 1 2 3 4. So this is the way again, and you see this is again the same. We have again we getting another subgroup, and that subgroup is again is by the S4. So this is again, this is this type of there, but these two subgroups we taking both are the for corresponding this Cayley 4 group and corresponding to the this multiplication group of 4 elements. They are two different subgroups we have to taking in this form, which is isomorphic to this subgroup permutation subgroup, and this one is equal to none. Okay, so now just I just take a one more example for a cyclic group of order 4, and then you have to just take in the form of this G can be written alpha to the power 4 is equal to identity. Again, if you write a construct a table of this, by the table we can construct this. Now indexes of this E alpha alpha square alpha cube we replace into this form. Then identify the permutation. Pi is generated by 1 2 3 4. G is isomorphic to the H of this form, and then clearly if you take just if you want you can just verify this the previous 3 examples. We have H is equal to E pi pi square and pi cube, and this is nothing but again as a 4 element, and this is again is a subgroup of this S4. So this means we have to show that various groups are taking in this form, and then we solve so many example and show that if I have a finite group, and then finite group is always is a isomorphic to some permutation subgroups of Sn of order n. That is the all for Cayley theorems, and these are the some examples related to the Cayley theorem. So I have to stop today's lecture here. I just complete this Cayley theorems also today. So in the next class we have to start the last topic of our course for direct products of a group. There is two types of direct products: is external direct products and internal direct products. And then in the end we have to show that the theorem for a finite groups is a Cauchy theorems and this form direction. So I just stop here today lecture, and we continue in the next lecture for direct products. Thank you very much.